Good afternoon, friends, and welcome to the session of the optics which I was discussing with you. And this is the chapter number 2, which is the most important chapter of the optics part. So my request is that please go to the chapter number 1, reflection. That was the first part of the reflection, and this is the second part of the reflection. So please take a note that this chapter we are doing the chapter number 2 for the optics, and chapter number 1, which was reflection of light, we have already discussed. Please go and refer to that chapter. Okay, so today we will be starting the refraction of light. As you all know, optics, this is the second part of the optics, which is the most important chapter. So let us go into it. Okay, so let's see. Refraction of light. What is refraction of light? It is the phenomena of change in the path of light when it passes from one medium to another. That means when light will pass from one medium, as you can see, when light is passing from one medium to another, when light is passing from one medium to another medium, suppose it is air and suppose it is water. So when light is passing from one medium to another, the light will bend from its path at the surface of separation. Okay, so this is called the refraction of light. This phenomena is called the refraction of light. Clear? Next, cause of refraction. Now, what is the cause of refraction? Very important. It is the change in the velocity of light. Change in the velocity of light when it passes from one medium to another. So when light is passing from one medium to another, what happens is its speed changes. Its speed changes. See, its speed will change. Its speed changes. So since the velocity of the light changes, so speed changes, and due to which what happens, that the light will change from its path. Clear? The light will change from its path. So now let us see. Whenever light goes from one medium to another, as you can see, light is going from the medium 1 to the medium 2. Whenever light is going from one medium to another, the frequency and phase of light do not change. Please note this. That the frequency and the phase of light, they will not change. The frequency and the phase of light will not change, but velocity and wavelength will change. The velocity and wavelength will change, but the frequency and phase will never change. Clear? Snell's law. What is it? The ratio of the sine of the angle of incidence. So see, sine I by sine R, the ratio of the sine of the angle of incidence to the sine of the angle of refraction, is a constant and is called refractive index of the second medium with respect to the first medium. Refractive index of the second medium. Light is going from first medium to second. So this is how we write. Light goes from first medium to second. So we call it refractive index. We will call it refractive index of the second medium with respect to first medium. Light is going like this, first medium to second medium. So we will call refractive index of the second medium with respect to the first medium. And what is this refractive index? It is sine I to the sine R. Sine I to sine R is the refractive index. Clear? Absolute refractive index. What is it? It is the ratio of the velocity of light in vacuum when the light is going from vacuum to any other medium. That means the first medium should be vacuum, and the second medium can be anything, suppose water or glass. So when the light is going from vacuum to any medium, it is called the absolute refractive. It is called the absolute refractive index. Okay. Next is, what is refractive index? When the light is going from one medium to another, means the first medium can be anything, the second medium can be anything but not vacuum, first medium can be anything. Suppose light is going from air to any medium. So suppose light is going from air to glass, or light is going from glass to water. So in this case we will call it as a refractive index. But when light is going from vacuum to this it will be called as a vacuum. When the light is going from vacuum to any medium, it is called absolute refractive index. Now we know the speed of light in vacuum, it is the speed of light in vacuum to the speed of light in the medium. Speed of light in vacuum is 3 into 10 to the power 8 meter per second, which is the maximum for any medium. So refractive index, absolute refractive index is always greater than only refractive index. Absolute refractive index is always greater than only refractive index, because absolute refractive index is C by V. Okay, and since C is always greater than any V, C is always greater than any V, that is why absolute refractive index will always be greater than refractive index of any medium. Please take a note of it. Next, refraction through a glass slab. So first, friends, see this. This is the light going. It strikes the surface of glass. It bends towards the normal because speed will slow down, and then it strikes again, and now the speed will increase because it enters the air. So this is the path of the light. This was the path of the light. Clear? So as you can see, it makes an angle I1 at this surface, angle of refraction here, first R1. Now I1 is equal to R1, I2 is equal to R1, please note it, and then it makes an angle of R2, and R2 is equal to I1. Please note that, because it is the same medium, air, it is coming out in air, it is coming from air, and it is coming out in air. So the angle of incidence at air and angle of emergence at the air will be same. Clear? So now, discussing this, so let us see refraction of light through a glass slab at L. So here, so it will be sine I1 by sine R1, and it will be, light is coming from the air to the glass, so it will be glass with respect to air. Similarly at M, light is going from glass to air, so glass to air, as you can see, so it will be sine I2 by sine R2, because it is always angle of incidence to the angle of refraction. Angle of incidence is I2, this is the angle of incidence at the second surface, and this is the angle of emergence at the second surface. Okay. Now if I multiply these two, we know that R1 is equal to I2, they will cut out, so, and I1 is equal to R2, as I told you. So we are getting this relation from here. We are getting A mu G equal to 1 by G mu A. That means If you know A mu G, that means if I know that light is coming from air to glass, okay, and this is what glass to air. So refractive index of glass to air is reciprocal of the refractive index of air to glass. Okay. Next is lateral displacement. So what is lateral displacement? So what is that lateral displacement? So let's see the lateral displacement. So as you can see, friends, this shift in the path from the original direction of the light is the lateral displacement. Clear? So it is mn dash, which should be T sine I1 minus R1 by cos R1. What is T? T is the thickness of the glass slab. As you can see, T is the thickness of the glass slab. I1, R1, these you know. So if we can put it in this formula, we will get how much shift the light has done when passing through the glass slab. Next is real depth and apparent depth. So friends, watch here. This is water and this is air. Clear? So when a light is going, suppose this is a coin. So light is going like this. It suffers refraction, so it will move away from the normal. And if I produce it back, here is the image. That means any person who is seeing here, he will feel that this object is actually here. This object is actually here. So it will appear raised up. It will appear raised up to him. It will appear raised up to him. Clear? So from that point of view, if you see this coin will appear raised up. Similarly, it is difficult to hit a fish underwater. Why? Because this is the actual fish and we see the image of the fish here. So if I try to hit this, then we are actually hitting the image. Similarly, water tank appears less deep. This is the actual depth of the water tank. But when I see from the top, I will feel that this is the depth. So it will appear less depth. It will appear less depth. Clear? So similarly, a coin appear raised up. If this is a coin here kept, I will feel that coin is risen till here. A coin will appear raised up. Similarly, a person's leg appears short. If a person is standing, his legs will appear only this much. This is the actual length of his depth of his legs, but I will feel that his legs are shorter. This is again due to the refraction of light. Letters appear raised up when viewed over a glass block. Suppose you have written some letter here. So this letter will appear here. So they will appear raised up. This is happening why? Due to the refraction of light. These all phenomena are happening due to the refraction of light. Clear? So now let's see. The ray is coming from the water to the air. So A mu W. Sin I by sin R. What is sin I? So as you can see, sin I, this is the sin I by sin R. What is sin I? Please watch here. What is sin I? If I take this triangle, sin I will be perpendicular by the hypotenuse. Perpendicular by the hypotenuse. Clear? So that is why we have written AB by OB. AB by OB. Similarly, if you want to find the angle, the sin R, if you want to find sin R, we will choose this triangle. So sin R will be perpendicular by the hypotenuse. So it will be AB by IB. It will be AB by IB. Now AB cuts, it is IB by OB. Now see IB. What is IB? Please watch here. This IB will be very much equal to AI. Will be IA. Will be very much equal to IA because the angles are very less. Because the angles are very less. So IB will be very much nearly equal to IA, and similarly OB will be very much equal to OA because the angles will be very small. Please take a note of this. So putting it, A mu W will be OA by IA. What is OA? OA is the real depth, IA is the apparent depth. Okay, so refractive index has got another formula, that is real depth by the apparent depth. So what is the shift? This is the shift. This is the shift. So shift is real depth minus apparent depth, and shift is proportional to the refractive index, as you can see. That means if the refractive index of the medium is more, if the refractive index of the medium is more, the shift will also be more. The shift will also be more. If the refractive index of the medium is more, the shift will also be more. Clear? Next, if the refractive index of glass and water, see this is refractive index of glass, so here it is given, refractive index of water given. I want to find what is the refractive index of glass with respect to water. Glass with respect to water. So this is the formula. Please note here, the lower part will be written up and the upper part will be written down. Please watch here. So dividing it, we get, this is the answer. Next is a small dot of ink is viewed through a glass slab of thickness 10 centimeters. So as you can watch here, this is given 10 centimeters. This is the thickness. This is the thickness of the glass slab. So thickness of the glass slab, this is given 10 centimeters. This is 10 centimeters. Clear? So if the thickness of the glass slab is 10 centimeter and the refractive index of the glass is 1.5, what is the shift of the dot? So we know that refractive index is real depth by apparent depth. So 1.5 is the real depth. Depth is 10 centimeters. Apparent depth, we find out it is 6.66. That means what is the shift? Real depth minus apparent depth, 3.33 centimeters. So the dot of ink will appear raised by 3.33 centimeters. Clear? Let's see, friends. Refraction of light through a compound plate. Please watch here. This is a compound plate. The compound plate, that means there are two plates, 1 and 2. So see how the ray of light is entering. First I will take from air to glass. So it is the air to glass. That means from A to B. A to B. So sin I by sin R1. Angle of incidence to the angle of refraction. Similarly B to C. So angle of incidence here is R1 and refraction is R2. So sin R1 by sin R2. Next is from C to A. So angle of refraction is R2. Angle of incidence is R2 and angle of refraction is I. Now if we multiply all these, we get it cut. That means this is our formula when the light is passing from two glass slabs together. Next, friends, we have a topic called total internal reflection. What is it? It is the phenomena of refraction of light into a denser medium from an interface of this denser medium and rarer medium. What is it? Suppose this is the surface which is separating air from water. So water is the denser medium. Now please keep watching. Suppose I take a ray which is hitting normally. So if any ray is hitting normally, it will go straight undeviated. Please watch here. If it hits normally, it will go straight undeviated. Second, if I take a ray which is hitting at an angle, this is the angle which is less than critical angle. This angle of incidence is less than critical angle. What is critical angle? Critical angle is the angle at which please watch here, critical angle is the angle at which any ray of light, if strikes, it will suffer refraction through the surface. That means angle of refraction will be 90 degree. Angle of refraction will be 90 degree. So critical angle is that angle at which a ray of light, if strikes the surface in the denser medium, the angle of refraction will be 90 degree. That is, the refracted ray will move along the surface. That is critical angle. Okay, so suppose here the ray strikes at an angle less than critical angle. So it will suffer refraction. Similarly, if a ray of light is striking at an angle more than critical angle, then the ray of light will reflect back into the same medium. Okay, so if it strikes normally, it will go straight. If it strikes at an angle less than critical angle, it will suffer refraction. If it strikes at an angle equal to critical angle, the refracted ray will move along the surface, and the angle of refraction will be 90 degree. And if it strikes at an angle greater than critical angle, it will suffer internal reflection. Clear? Okay. So, seeing all this, we find out the two essential conditions for total internal reflection. That means for total internal reflection, what are the two important things? Number one, what are the two important things for total internal reflection to take place? Number one, light should travel from a denser medium to a rarer medium. As you can see, for internal reflection, light should travel from a denser medium to a rarer medium. Second, angle of incidence in the denser medium should be greater than the critical angle. That means it should strike at an angle more than the critical angle. It should strike at an angle, as I showed you, that it is striking at an angle more than the critical angle. This angle, it should strike at an angle more than the critical. Then only it will bend inside the medium. This is the reflection. So it should strike at an angle more than the critical angle. Okay. Similarly, this definition is very important. What is critical angle? It is the angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree. Okay, you see, as you can see from here, it is the angle of incidence, this angle, at which the refracted angle will be 90 degree. Clear? Okay. So friends, let's see next one. In total internal reflection, 100% of the incident light is reflected back into the denser medium, and there is no loss of energy, intensity or energy, while in reflection and refraction there is some loss of intensity. That is why images formed by total internal reflection are much brighter than those formed by reflection. Okay, so in this internal reflection, as you can see, the total energy will be reflected back. Total energy will be reflected back. That is why the image formed by total internal reflection is much brighter than formed by refraction, or reflection. Clear? Because here there is no loss of energy. No loss of energy. Clear? So friend, let's see the relation between the refractive index and total internal and the critical angle. The relation between the refractive index and the critical angle. So this is the relation where C is the critical angle. C is the critical angle. Okay, so please note it. C is the critical angle. So this is the relation between refractive index and critical angle of a medium. Find the minimum angle of incidence, that means the critical angle, so that a ray is traveling from glass to water does not emerge out. Please watch here, they want that the ray should not emerge out. So ray is going from glass to water. That is why I want water with respect to glass. I want water with respect to glass, and that is why I told you that water should be up and glass refractive index should be down. So that this is the refractive index of the water with respect to glass, but I need glass with respect to water. Please be very careful. If the ray is going like this, total internal reflection C. So what do we write? This is air, this is glass. So what do we write? 1 by sine C. So please watch here that the ray of light is going from glass to air, but we have to take refractive index of glass with respect to air. So here the ray of light will go from, here the ray of light will be going from glass to water. Glass to water. So we want water with respect to glass. We want water with respect to glass. Clear? So based on this, we have calculated the sine C, and we got it is 62.7 degree. That means if the ray of light is hitting at 62.7 degree in the glass medium, the ray will not go out but come, it will suffer internal reflection. Applications of total internal reflection. So there are, see, as we all know, there are certain applications of total internal reflection. Number 1 is brilliance of diamond. Number 2 is mirage. Number 3 is totally reflecting prism. And number 4 is optical fibers. These are some very important applications. So let us see them one by one. Brilliance of diamond. The refractive index of diamond is how much? 2.42. 2.42. So when diamond is cut, so when diamond surfaces are cut, please take a note. When diamond surfaces are cut in such a way that if a ray of light is entering inside diamond, it will always suffer total internal reflection. It will always suffer, it will always hit at an angle more than 24.4 degree. It will always hit at an angle more than 24.4 degree. So due to this multiple reflections, it causes brilliance. It causes the brilliance. So when a ray of light is entering inside diamond, when a ray of light is entering inside the diamond, it will always hit at an angle greater than the critical angle. It will always hit at an angle greater than the critical angle. Okay, and suffer multiple reflections, and due to which it is causing the brilliance. Next, mirage. So in mirage, what happens? In hot desert, when the ray is coming from, suppose, a tree, the air medium is very, very hot at the surface and little bit cooler at the upper parts. So the refractive index changes. So the light keeps on suffering bending, light keeps on suffering the refraction till it strikes at an angle more than critical angle. So it will reflect back. And when a person sees this, he feels that the light is coming from here. So he sees the reflection of this tree and feels that there is some water here. So this is called mirage. It is due to the bending of light when it strikes the surface, hot surface, at an angle more than critical angle and will reflect back. So when the rays are received by the observer, he feels that the ray is coming from here. So he sees the image of this tree and feels that there is some water here. So this is called mirage. So now let us see the next one. Totally reflecting prism. As you can see, the rays are striking. We should always know that the critical angle of glass is 42 degree. Please note, critical angle of glass is 42 degree. So wherever it strikes at an angle more than 42, the rays are getting reflected back. See here. So this is called totally reflecting prism. Similarly, when a ray of light is striking here, it is striking at an angle 45, which is more than 42. Again striking at an angle more than 42. So this ray is same thing. So see the image which was upright here, is now inverted. So this is due to the totally reflecting prism. Similarly, in optical fibers, the optical fibers are made, the material is of low refractive index and the inside material is of high refractive index. So when any ray of light is striking inside, it always strikes at an angle more than critical angle, more than critical angle, more than critical angle, more than critical angle here also. So always there will be an internal reflection and the light coming out from here will have the same intensity. So there will be no loss of any energy inside when the light passes through the optical fiber. Clear? Next is assumptions for spherical refractions through mirrors. Through mirrors, what are the assumptions we will be doing for doing any calculations part with the mirror sums? Okay, so let's find out one by one. Number one, all distances are measured. All distances are measured from the pole of the mirror. That means any distance you measure will be from the center of the mirror. Any distance which you want to measure, it will be from the center of the mirror. Okay, number one. Number two, please note these very, very important things. U is always negative. U is always negative. Next is, please note, V. If it is a real image, it will be negative. If it is a virtual image, it will be positive. If it is a real image, it is negative. If it is a virtual image, it is positive. How will you know real image? Real image will be always inverted. Virtual image is always upright. Okay, so if it is a virtual image, you will take V as positive. If it is a real image, you will take V as negative. Similarly, let us see. Height of the object is always positive. Height of the image. Now for the height of the image, height of the object is always positive. Height of the object is always positive. And now for the height of the image. If the image is a real image, it is positive. If it's a virtual image, it is negative. If it's a real image, it is positive. If it's a virtual image, it is negative. Similarly, convex mirror's focal length is positive and concave mirror's focal length is negative. Please note these, which are very, very important for your sums part. Okay, so now let's see. Now let us move to the next part. Refraction. We are studying refraction through a convex or a concave mirror. We will do refraction through a convex or a concave mirror. Okay, so please watch it very, very carefully, what I am telling. First, we are doing when the object is placed in the denser medium. When the object is placed in the denser medium and real or virtual image is obtained. When the object is placed in the denser medium and real or virtual image is obtained. So watch it. Suppose this is the mirror. Okay, this is the denser medium and this is the rarer medium. This is the rarer medium and the object is placed in the denser medium and the image is obtained. The image is obtained either here or here. So what is the formula for this? Please watch it. What is the formula for this? Please keep a watch on this. This is the formula. mu2 by minus u is equal to mu1 minus mu2 by r. Mu2 by minus u is equal to mu1 minus mu2 by r. This is the object distance, this is the v, u is the object distance, v is the image distance, mu2 is the refractive index of the denser medium, and mu1 is the refractive index of the rarer medium. So, and r is the radius of curvature of the mirror. R is the radius of curvature of the mirror. Clear? Similarly, when the object is placed in the rarer medium and a real or virtual image is obtained, please watch here. Object is placed in the rarer medium. Rarer means mu1, and the image obtained is a real or virtual, that's not the factor. So you have to watch here. This is my formula. So that means if you watch very carefully, you will be able to understand. Now the object is placed in the rarer medium. Previously it was placed in the denser medium. Previously it was placed in the denser medium. So please watch here. This is the formula when the object is placed in the denser medium, and this is the formula when the object is placed in the rarer medium. If you watch here, see, mu1 and mu2, they interchange their places. They interchange their places. If you watch mu1 and mu2, they will interchange their places. One thing, R is positive for a convex mirror and negative for a concave mirror. Negative for a concave mirror. Clear? Next. So let's see a sum. Light from a point source in air. So the point source is in air, that means rarer medium. Falls on a convex mirror, refractive index given. Radius of curvature given. Find the position, so find the V of the image when the object source is 1 meter. That means this is U from the mirror. So the light is coming from the rarer to denser. So rarer to denser, we will choose this formula. As I told you that you have to be very careful in choosing the formula. So because it is rarer to denser, so we will choose this formula. Now choosing refractive index of the rarer medium is always 1. Please keep note of this. Denser medium is given 1.5. U is always negative, which is minus 100, 1 meter. And we are finding, and radius of curvature is 20 centimeter because it's a convex mirror. So it is a convex mirror, so we have to take R as positive. So putting the values, we get the V as 100 centimeters. Clear? Next, what is the radius of curvature of a concave surface? Please note, it is a concave surface. Okay. Refractive index given for a virtual image at 40 centimeter. So this is the V given. U given. U is placed refract from, now it is object is placed in the rarer medium, so mu1 is 1 and mu2 is 3 by 2. 3 by 2. So it is coming, that means we are using the relation. Please watch here. We are using the relation that the object is placed in the denser medium. We are using the relation that the object is placed in the denser medium. Clear? 1 minute. We are using the relation that the object is placed in the denser medium. So watch, denser, object is placed in the denser medium. So here is the object in the denser medium. See, this is the object in the denser medium, and here is the image. So it's a virtual image, but I told you, you just have to keep note where is the object, in the denser or the rarer. So denser to rarer, I will take denser to rarer, and this is our formula. Putting the mu2 is the refractive index of the denser medium. U is negative. Rarer medium is air, so 1. V is given. It is a real image. That means V is minus 40. So we are finding the R, which is coming 1 by 0, which is infinity. Which is coming infinity. Clear? Next is, friends, let's see lens maker's formula. It is one of the most important formulas of physics, and it has come immense number of times in the board examination. Every year this is a question, lens maker's formula. So let us see how to derive it, which is very, very important. So see, this is a convex lens. This is the rarer medium. Rarer medium is mu1, denser medium is the lens glass mu2. Again, this is the rarer medium mu1. So here there are two surfaces. So at surface 1, which is rarer to denser, we have used this formula. Similarly, at surface 2, which is denser to rarer, we have used this formula. Now please watch. In the surface 1, what is the object distance? U. What is the image distance? V1. Because due to the first surface, this is the image formed. This is the image formed due to the first surface. So its image distance is V1. So putting in place of V, see, we have put V1. And let the radius of curvature of the first surface be R1. Similarly, at the second surface, now this is my object distance. This is my object distance. And this is my image distance. This is my final image distance, which is V. So now putting it in the denser to rarer formula, this is my U and this is my V, and this is the radius of curvature of the second surface. So adding both the equations, as you can see, this will cut out. If I add both the equations, this will cut out. So basically we are left with this, taking mu2 minus mu1 common, this becomes minus R2. Now what we have done, we have divided by mu1. We have divided the equations. It is dividing by mu1. So we get 1 by V minus 1 by U equal to mu2 by mu1. Now what is mu2 by mu1? Mu2 by mu1 is the refractive index. It is actually the refractive index of the glass with respect to the air. Okay, this is actually the refractive index of the glass with respect to the air. We get this. So this is our formula of the refraction through the two surfaces. Please note, very important formula. It's a very, very important formula. Now if I see that if U is infinity, if object is kept at infinity, we all know that image is formed at the focus. Please keep note on this. If the object is kept at infinity, the image is formed at the focus. If the object is kept at infinity, the image is formed at the focus. Now using this, we have found out that this is the 1 by, in place of 1 by v I will write 1 by f, in place of u I will write infinity, so 1 by infinity is 0, so we get this, so 1 by f, this is the actual lens maker's formula. This is the actual lens maker's formula. So please keep a note of this, very, very important. Next, let us see lens maker's formula for a concave lens. For a concave lens, lens maker's formula for a concave lens. That was for a mirror and now it is for the concave lens. So as you can see, we have chosen the concave lens here. So this is my object, and due to the first surface, this is my image. So what is the object distance u and image distance is v1. So applying this from rarer to denser, we are applying it for rarer to denser. We are applying it for rarer to denser. We are applying it for rarer to denser, and we get this. U is our object distance, rarer to denser, so mu1 to mu2, and the image distance is v1, and for the first surface, the refractive index, the radius of curvature is r1. Now for the second surface, which is denser to rarer, second surface which is denser to rarer, as you can see that now my object distance is v1, this is my object distance, and this is my image distance. This v is my image distance. It is denser to rarer, so we are using, this is my u and this is my v, and for the second surface, okay, R2 is taken as the, this is my first surface. Please note here, this is my first surface. The ray will suffer refraction from the first surface. So my R2 is taken as negative. So now adding both the equations, as you can see, when I add both the equations, this will cut out and we are getting this equation. So dividing by mu1, we are getting this. And now if u equal to infinity, v is equal to f. Already we have done this. When u equal to infinity, v is equal to f. So putting it, we are getting 1 by, as you can see, on putting it, we are getting 1 by f equal to minus 1 by infinity. So we are getting, this is the lens maker's formula for a concave lens. This is the lens maker's formula for a concave lens. Clear? So friends, now let us see the next one. For a double convex lens, please watch here. For a double convex, what is a double convex? This is a double convex. R1 is positive and R2 is negative. For this surface, I have to take this side, and for this surface, I have to take this side. So it is against the ray, which is negative. It is towards the ray, which is positive. And focal length is positive. Please note all these points, which are very, very important for us. R1 is positive, R2 is negative, focal length is positive. For a double concave lens, how will it look? It will look like this. Okay, here R1 is taken as negative, R2 is taken as positive, focal length is taken as negative, just the opposites. Now let us see, friends, let us do some numericals. The radii of curvature of a surface of a double convex lens, this is R1, R2, focal length. What is the radius of refractive index? So using this formula, it's a convex lens, so focal length is positive, refractive index is given to us, R1 is positive, R2 is negative. Putting the formulas, we are getting the refractive index as 1.66. This is how we get the thing. R1 is positive, R2 is negative, focal length is positive. Putting in this lens maker's formula, we get this. Next, find the focal length of a double concave lens. It is a concave lens. So we know R1 is negative, okay, and R2 will be positive. R2 will be positive, R1 will be negative. Refractive index is given, surrounding medium is air. So using this formula, as we already know, using the lens maker's formula, and because it is a find the focal length, so focal length should come in negative because it is a double concave, it is a concave lens. So using this formula, we can get the answer. Next, lens formula. So please watch here how to get the lens formula. How to get the lens formula now. So first we are trying to do, we will be doing both for a convex lens and concave lens. So let us see. This is the convex lens, friends. This is the object kept at a distance u. This is the image at a distance of v. So please watch here the triangles which we are taking. We are taking this triangle and we are taking this triangle. These two triangles are similar, so we will write, these two triangles are similar, so we will write a dash b dash by AB equal to CB dash by CB. Okay, now we are taking this triangle A dash B dash F. So see, watch here, this triangle we will take and this triangle we will take. They are also similar. So we will take A dash B dash by CD equal to B dash F by CF. So now you see here, in both the places we are getting A dash B dash by AB, A dash B dash by AB. So making these two equal, we are getting CB dash by CB equal to FB dash by CF, FB dash. So see, FB dash, this how we can write? We can write B dash C minus CF, CB dash minus CF. We can write like this. So now CB dash is what? V. CB dash is the V, and CB Please watch here. Where is CB? Here is CB. CB is the U, which should be negative. CB dash is a real image, so it is positive V. CB is an object distance, which is minus U. CB dash is V, so and CF is the focal length. Focal length is positive. Okay, here U is taken as negative, V is taken as positive, F is taken as positive. So putting these values and dividing by UVF on both sides, we get this formula. This is the lens formula, convex lens. Now let us see concave lens. Now we are choosing this A dash, B dash, we are choosing this triangle, and we are choosing this triangle. Okay, so now these two triangles are similar, so we can write A dash B dash by AB. So please watch here. A dash B dash by AB equal to CB dash by CB. Similarly, in triangle A dash B dash F and this triangle, the triangles are similar, so we can write A dash B dash by CD equal to B dash F by BC by CF. Now taking these two similar, so we can write down, see, as you can see that CD and AB are equal. CD and AB are equal. So instead of this CD, I can write AB. Clear? So basically these two become same, and we write A dash B dash by AB equal to, that means instead of this we write A dash B dash by AB is equal to B dash F by CF. Now equating these two A dash B dash, equating these two A dash B dash, what we can do now is, so we are equating it, so we are getting this B dash F. What is B dash F? B dash F will be CF minus CB dash. Now as is given here, CB equal to minus U, CB dash equal to minus V, CF equal to minus F, putting the values and then dividing by UVF, we get this is the formula for the focal length of a concave lens. Clear? Now friends, linear magnification, what is it? Height of the image by height of the object, or it is V by U for a lens. Mind it, this is for a lens. Height of the image by height of the object, which is V by U. Similarly, the power of a lens, it is the reciprocal of the focal length expressed in meters. So this is the power, 100 by F. SI unit of power is diopters, and please note here, power is positive for convex lens and power is negative for concave lens. Please keep this in mind. combination of lenses. What is it? Suppose we have got two thin lenses which are combined like this. Focal length of this is f1, this is f2. Clear? Now if it is both are convex, then this is the formula. If both are convex, please note the formula. If both the lenses are convex, this is our formula. If one is convex, one is concave, then this is the formula. One is convex and one is concave. Which is convex, that is plus, which is concave, that is minus. Now please watch here, very important thing, that is, if f1 is equal to f2, then in this formula, if f1 is equal to f2, please note here that 1 by f is coming 0. So focal length is infinity and the combination of the lens behaves as a plane glass, because focal length is infinity. So combination of the lens will behave as a plane glass. If the focal length of the convex and concave lenses are equal, please watch here, if the focal length of the convex and concave are equal, then according to this formula 1 by f is coming 0, so f will come infinity. That means the combination will behave as a plane glass. Similarly, if f1 is greater than f2, then what happens? 1 by f will be less than 0, 1 by f will be negative. So it behaves as a concave lens. Please keep these things in note. If f1 is greater than f2, then 1 by f is coming negative and the combination behaves as a concave lens. Similarly, if f1 is less than f2, 1 by f is positive and the combination behaves as a convex lens. So please keep note of this. These are important for your conceptual as well as numericals. Very, very important, please. So friends, with this we cover up the optics chapter 2, and I hope you have understood it, and please follow the theory very nicely. Please 2-3 times you see the theory and note down the important formulas. I have discussed some numericals also, so I would request you, please follow the thing very nicely, and my lectures, please go through it, note down the notes, note down the formulas, do the sums on your own, then only you will be able to understand it properly. Okay, so with this we have completed the chapter 2. We have completed the chapter 2 of this, and I hope that you have understood this. This is the chapter 2, we have completed it. Optics chapter 2, we have done some numericals. So please go through it very nicely, and please note the notes whatever I have discussed here. Okay, so friends, with this we end this session of the refraction of light optics chapter 2, and I would request you, please follow Parijat sir classes, and definitely subscribe my channel, so that I get more and more motivation to make more and more videos for you, which will be helping out you for your board exams. Okay, so thank you very much for watching this, and let's meet again for the another session which I'll be soon uploading it. Thank you.